Good afternoon. Thank you for joining us live from NASA's Kennedy Space Center in Florida. I'm Cheryl Warren in the Office of Communications. We're here live with an audience who is excited to see a launch. Am I right? Woo! Welcome. We're here today for What's on Board to discuss some of the science that's headed to the International Space Station. Launch is targeted for April 18th at 11:11 a.m. Eastern from Cape Canaveral Air Force Station in Florida. Today, we'll have a number of guests that come up and talk to you about the exciting science that we're sending to station. I will ask questions from the audience as well as online. So if you're following us on social media, please use the hashtag AskNASA. Our first guests today are Dr. Tara Rutley and Dr. Mike Roberts. Tara?
Great. So thanks, everyone. I'm not kidding when I say it's really fun to be here at the Kennedy Space Center. You sound like you're already pumped up. Got me pumped up, too. Seems like you've seen some really interesting things today so far, right? Yeah, this is a really great place to be right before a launch. You get to see some of the science processing facilities. I'm from Houston, Texas at the Johnson Space Center. I work in the Space Station Science Office. I heard a woo, yeah. Yes, so I have the coolest job, I think, here. We'll talk about that. Because I get to see all the science that comes across and heads for the space station, including the National Lab science that Mike's going to talk a little bit about. So I've gotten a chance to speak to some of the scientists who are here today, whose payloads are going up on this next launch. And they're ready to talk to you, so it's going to be an exciting hour. To give you just an overview of Space Station, you all know, I think, for the most part, that it is a laboratory. It's a research laboratory in space. Now's the time to use this laboratory as a way to test out some of the systems and do some research involved in how we go and explore beyond the Earth orbit. There's lots of human physiology we need to understand. There's lots of technology development. There's food production that you're going to hear about. Things that we need to take the time now to use the laboratory to move forward. But, I mean, it's also a platform by which it gives us a unique environment to try new things we haven't done before, to do new studies that might elucidate some mystery, to help us improve our ways of treating disease, or how we approach our aging process, and how we create new materials for use here on Earth too. So it's got some Earth benefits that we're already starting to receive. So it's a unique platform. You already know there's nothing like it anywhere else. All of our partners across the partnership, JAXA, ESA, CSA, Roscosmos, us, all participate in the research, so we share in that. We all have goals for human exploration, goals for Earth benefits. Right now, I think this orbital launch is going to enable the continuation and some new investigations of about a little over 250 science investigations over the next 6 months. And that's, crazy. And it represents like almost 1,000 scientists from around the world. So the women and men that are up there now and who are going to be headed up there over the next 6 months will be busy doing all of your research in a way that's going to bring around the benefits that we all are looking to see. And so today, you're going to hear from some groundbreaking scientists who have never done anything what's about to be done on the space station before. And it's also going to pave the way for new capabilities. Particularly interesting are the new capabilities that are being added for molecular biology, and some studies of some of the changes that happen in physiological or living systems at a level you can't see all the time, but they're still always happening. So new capabilities for new scientists, and some technology development too, such as crystallizing different materials that could be used as radiation detection devices and such. So it's leveraging that microgravity environment, I think you all know, to be able to bring the benefits back home to us, and to allow us to explore further. And with that, I'll pass along to Mike Roberts.
Thanks, Tara. So Tara is here representing NASA, and NASA is obviously one of the primary real estate owners and operators of the International Space Station in partnership with the international partners. There is also on the International Space Station an orbiting national laboratory, the ISS National Lab. And the ISS National Laboratory is managed by a non-government organization, CASIS. That's who I'm here representing, the Center for the Advancement of Science and Space. Our mission is to work with NASA to offer opportunities for access to the International Space Station, to the space environment. So as Tara mentioned, the International Space Station is an orbiting laboratory. It's also an observatory. You've seen lots of pictures, I think, of Earth from the International Space Station. It operates in a unique environment that enables it to be utilized not only as a laboratory, because you have 24 hours, 7 days a week, 365 days a year free access to microgravity, which has very profound effects not only upon large organisms like humans, but also it affects even the smallest among us, the viruses, the bacteria, the archaea that live within and on us. And a lot of those molecular tools that Tara was highlighting upon are of interest to NASA. As we move farther away from low Earth orbit and go deeper into space, we need to take with us tools that we can monitor the health not only of the humans that are there, but also the health of the physical environment of the microbes that are associated with them. And you're going to hear a little bit about some experiments that are going to be conducted by students today who are utilizing cutting-edge molecular tools that will inform us about the environment's effect upon aging as we travel into space. In addition to being an observatory and a laboratory, the International Space Station National Laboratory is also a platform for innovation. So there are opportunities for STEM education. There are opportunities for students to not only participate in scientific experiments, but actually to propose experiments that they want to do in space. You'll hear more about one of those today. It's also a platform for innovation for companies, both large and small. So one of the main focus areas for the International Space Station National Laboratory is to enable access to space environment for commercial organizations who see in space a benefit to their product line or to areas of research and technology development that are currently engaged in. You'll hear a little bit about that today as well from companies that are interested in developing new scintillation crystals for radiation detection that can be used here on Earth or in space. You'll hear more about opportunities for small satellite launching opportunities through one of the implementation partners, NanoRacks. You'll also hear a little bit more about opportunities for materials testing in that environment. And you'll hear about some experiments that are focused on bringing those fundamental understandings of life and microgravity down to the physical level and the molecular level. And there are a lot of tools that are available to do that now that are being improved by actual utilization in the space environment. CASIS is not only focused, however, on the commercial side, we also work with other government agencies. Those are government agencies in addition to NASA, like the National Science Foundation, the National Institutes of Health, who are also seeking to exploit low Earth orbit for science investigations.
That's all great, Dr. Mike. Do you actually have a video for us by chance?
I do. I have a short video we'd like to show you about the scintillation crystals experiment that's going up on OA7.
So why do humans care so much about science? Why are we so intrigued by research and learning? We're problem solvers. We want to dig into it and dissect it. We are just that kind of inquisitive people, trying to answer the question of why and how and maybe when. The first 10 years of the station were all about assembling it. We now have the opportunity to do research at a broader scale, a higher level. At any one time, there could be 200, 300 different experiments going on.
RMD has developed this new crystal, which is a scintillator. Scintillators are crystals which emit light when they are exposed to radiation. An experiment like ours, we can use universal hardware and platforms which are already on the space station. There's a huge excitement factor. You feel like you live in a science fiction movie.
We're really working hard, both sides, NASA and National Lab and CASIS, to get new users to come in and do your world-class science on the station.
Excellent video. Speaking of how and why, do we have any questions from anyone in the room for Dr. Rutley or Dr. Mike Roberts? Who's going to be brave? How about first row?
What training do student scientists need in order to make their way to your offices or your projects?
So first of all, the orange flight suit did not throw me at all. It didn't even shock me, but it's so cool. So very cool. So students come from many different areas, and mostly most of the students for Space Station come through the National Lab effort. Dr. Mike will share that with you. But also, if you look up STEM on Station, there are lots of opportunities for students to participate in Space Station activities through there. But I'm going to let Mike share with you some of the specifics about student involvement.
Yeah, so I would say the one most important thing is imagination. It's about thinking of an idea, something that you think, how is this going to happen in the space environment, and bring that idea to it. So there are opportunities that can touch children at any age, from story time in space, we talked about briefly before. There are opportunities to simply enjoy an astronaut reading a story and understanding the way that life occurs in the space environment. I have two children, one who's 20, one who's 13. The younger one has never lived in an era where there were not humans in space, right? The 20-year-old, he's an old guy now. He grew up not knowing that humans were in space all the time doing cool stuff. There are opportunities through programs like challenge programs that offer opportunities for students to design payloads. There are opportunities for older students to actually begin designing small satellites where they not only can form a team that actually assembles the electronics and the actual part of the hardware, they can actually design experiments that go on inside them. So we're entering that realm now where space is accessible to everyone. It's not just a focus of the space agencies and the questions they have. It's really going to be at a point, not in the not too distant future, when you can probably go to some online ordering company and design your experiment and send it up for a reasonable amount of money. The way that we tend to operate in laboratories now, we send a lot of the analyses outside now, and all we're going to do in the future is add more opportunities for space science to that.
Those are really good points. And also there are opportunities through the Sally Ride EarthCam. If you look that up, it's managed by the U.S. Space and Rocket Center, and you can request imagery of certain areas from the space station. And then there's also the ISS ham radio opportunities too. So if you've got some ham radio enthusiasts, there are opportunities to get a group together and perhaps talk to the astronauts on space station with a ham radio. And like Dr. Mike said, you know, I think if you're a student and you can think of any science experiments you've ever done, and you think of how it might behave if you take gravity away, I think you'll find that you might be coming up with some really new creative, innovative ideas that Dr. Mike was referring about.
Great. So we do have 2 microphones in the room, so please do let us know who you are and where you're from as well.
My name's Debbie Reynolds. I'm from Pittsburgh, Pennsylvania. My question is about all the experiments that are going on up at the space station. So obviously all of the crew members that are there come from varied backgrounds. So what kind of training do they have to be able to run all those different experiments? Obviously they're not all biologists or physicists or things like that. So I'm curious about that, how they all get accomplished.
Right. So all of the astronauts who participate or fly up to the space station get trained in some aspect of the science. So usually payloads or the science experiments are assigned to crew members in advance, and they'll spend part of their 1.5-year training period. It'll be heavy on the science too. So they get trained specifically with the experiments that they're going to be working on. And that means they may get to know the principal investigator, depending on how complex the experiment is. And all of our partners go through that. Once they're on orbit, they are proxy scientists, and so they actually work with our lead increment scientists on the ground here, but they also have an opportunity to call the principal investigators too from space and work through issues with them, or maybe additional runs of an investigation with the PIs. So lots of opportunity to make sure that I'll tell you one thing: the astronauts absolutely own the science. They take full responsibility for it. That's what they care about on orbit. That's their job, and so they are fully vested in the science on station.
I know we have other questions in the room. Do we have any questions online right now? Again, if you want to submit a question, please use the hashtag #AskNASA. Take one.
Okay, so how do you ensure that the research, info, articles, data conducted on board the ISS are accessible to the public?
Okay, so I think both of us can address that. But if you go to nasa.gov/ISS-science, that's a repository of all the investigations that are performed on space station. We keep all content, and in that we also include a listing of the results, publications, scientific publications. But while that's our core, we also put out lots of communication products, such as web stories. You can follow us on Twitter at ISS_research. And so some of the fascinating results that come from space station science go out on social media. Also, they are posted on the ISS Facebook page. We do a lot of outreach. But really, our focus is to make sure that the public knows as much as possible about the benefits that are coming back to you, and about benefits for exploration for space, too. But we try publicly at the website, and then we take it from there by spinning off lots of different communication products.
Yeah, and there's information available on a couple of different websites for CASIS and ISS National Lab payloads. The most important one is to go to spacestationresearch.com. There's information on there that will provide you details about the capabilities that are there on station. It will have links to the publications that not only came from ISS National Lab, but from previous investigations that predate ISS National Lab. And there's a lot of opportunities just to ask questions. Part of CASIS's mission is taking the capabilities of research in space to a whole new audience. So we spend a lot of time at destination station events in partnership with NASA, speaking to communities about opportunities there. And we also have a very active STEM education program. So there's a lot of opportunities to learn about what's going on station. As a non-governmental organization, we also publish an annual report, which has lots of boring statistics and numbers in them. But there's information in there on all of the science and technology that's going up to station each year.
All great questions, and I know there's many more in the room. However, we do have a number of other guests with us today. So if you don't mind, let's give a round of applause to Dr. T and Dr. Mike. Thank you. For our next guest, we're going to hear from Dr. Howard Levine and Brian Onate to discuss the advanced plant habitat.
Thank you.
More applause, thank you.
I think there's 3 of them.
So I brought a visual aid. This is a plant called a Arabidopsis, not your average plant. This is actually the most used plant for basic research on Earth and on the International Space Station. So the first science experiment that's flying on the advanced plant habitat will be using a Arabidopsis. And if you have any further questions, I can elaborate later. I'm the project scientist for the advanced plant habitat. But why don't we go to the slides, if we could? This is Brian Onate, by the way. He's the project manager for the project, which has been 4 years in the making.
4 years in the making. So good afternoon, everyone. Project manager, what an exciting time to be actually flying this payload after working on it for many years. We had a white piece of paper when we started. They said, go build this, maximize the plant growth or the science area as much as possible, minimize the resources around it. That way we can grow plants from seed to seed and grow the largest plants we can on space station. So it's very exciting for us. If we go back to the slides real quick, what you saw in the picture there was our high fidelity prototype, and we call it the Engineering Development Unit, the EDU. Everything is an acronym at NASA, the alphabet soup that is out here. I'm just going to talk real quick about it, starting from the, I guess, the left, working my way right. On the very left, there are 3 main components in there. I'm going to talk about 2 of them, and I'll talk about the last one at the very end. We have our power system in there, and we have our water system for our plants. Moving our way towards the middle, you see that where the pink light is, that is actually the growth chamber. Again, it'll be the largest plant chamber, environmentally controlled chamber on the ISS, which is very, very exciting to have that capability up there. On each side of the chamber, you see these little modules on the side. That's actually our temperature and humidity control. And it actually allows us to control the temperature and humidity at various levels for the plants that they need. On the bottom corner, on the left, you see a drawer. That's part of the International Space Station that we got. In there we have our reservoir where we have our water, and we also have our CO2 tanks. And obviously you see the pink lights. We also have a lighting system. It goes up to about 1,000 micromoles, which is a scientific term that I will let Dr. Levine talk about. But it actually, we have the capability of producing about half the sunlight that you see. So if you were to go outside today, it's a pretty powerful light. And the mystery box, well, in NASA we have to give acronyms and everything and try to make it as cool as possible. We have a farmer. It's PHARMER. It's the Plant Habitat, Avionics, Real-Time Management, and Express Rack. And there will be a quiz later to see who remembers that. So we have a farmer. What does the farmer do? Well, the farmer's in charge of running the whole payload. We basically run about, I would say 90% of the payload from the ground. We need the crew members to put water in the system for us, do some maintenance activities for us to remove some filters, basically just make sure that the chamber or the payload is ready for all the plants. So it's an exciting time for us. I'm so glad that we're going to launch this very soon and give a lot of capabilities. And with that, Dr. Levine, he's going to talk to us about some of our first experiments we're going to do.
So if we could go back to the slides, please. So this is wheat grown within this EDU that Brian was talking about. So we're flying up the hardware on 2 rockets. We're flying it up on OA7 and then SpaceX 11. So the hardware will get to station. It'll be put together. There'll be a checkout. And we're going to do a test germination of 2 species. One is wheat, and the other one is, what's this called?
Arabidopsis.
Arabidopsis. You fail. So this is wheat. Let's go to the next slide. So this is Arabidopsis. Again, it's a much smaller plant. We start off putting multiple seeds in each location to make sure that we have good seedling growth and development. And you're going to see the next slide, we're going to be thinning these out. So now we're down to 1 vigorous seedling per location. Next slide, please. So here they are. They've grown a bit more. They're at what we call the rosette stage. Next slide. Here they are. It's just about week 4, and you're beginning to see the shoots. We call it bolting. The shoots are sprouting forth upward, and you can even see the beginning of flower development at the top of the shoots. Next slide. So this is at about 4 to 5 weeks, so much more stem and flower development. Next slide. And then this is what it looks like after 6 weeks. So the great thing about Arabidopsis is it goes from seed to seed in 5 to 6 weeks. So that's a very short generation time. And it's also been completely sequenced for its DNA. So we know all of its genes. There's an incredible database in terms of when its genes do different things. There's hundreds, if not thousands, of strains of Arabidopsis, each one tailored for a specific purpose.
Great. With that, we'll open it up for questions. Right here. Oh, 1 second.
Hi, I'm Megan Schaller from Indianapolis, Indiana, and I teach 5th and 6th grade science, and I wanted to ask you, you said you started with a blank sheet of paper, and now you have this very amazing piece of equipment. I teach my students the STEM and the engineering design process. Can you kind of comment on some of the skills that your team has used? Was there a lot of teamwork, collaboration, communication, testing over and over? What are the skills that are needed to get from a blank piece of paper to something this impressive?
Absolutely. Good question. Yes. Very challenging. So NASA, we have a lot of engineering experts here. But first, we started with our scientists, right? We went to our end. What I've come to find out is my customer. It's what I've learned through the process. He's my customer. I went to him, asked him, what do we need to develop? What do you need? He gave us a list of requirements. We also partnered with cases. So we went to our commercial partners and said, if we had this capability on ISS, what could we do? So we started with that. We used engineering, technicians, scientists. It wasn't just a NASA effort. We also worked with Orbital Technologies Corporation. They're a company out of Madison, Wisconsin. And again, they had engineering, technicians, scientists. So we partnered with all of them. And what is really cool, if the picture you saw with the growth chamber, it's about the size of a mini fridge that you might have in your office. You know, that's as big as we can make it. Our local engineers actually fabricated that. They built the shell here locally. We machined it. So we, NASA, take a lot of pride because the science that's going in there was actually fabricated here by engineers at Kennedy Space Center. So very exciting. It takes a collaboration, skills all across the board to make this happen.
But the scientists are his customer.
The scientists are my customer.
Right here in the front row.
Hi, I'm Claudette from Fort Lauderdale. I wanted to ask you, I mean, there are so many plants that you could choose from. How do you weed out which one? Had to throw it in there. How do you weed out which ones you want to use, which ones would work, that kind of thing?
So most of the science that flies on the International Space Station is what we call peer-reviewed science. So NASA puts out a solicitation saying, well, we're interested in this kind of research, and then scientists from all around the country submit proposals, and they submit proposals for a particular species. So it happens that about 80% of the proposals are with Arabidopsis. Better, a little bit better. However, as we get more and more into the exploration mode, we're beginning to shift into food-producing species, especially when we want to do what's referred to as bioregenerative life support systems, where we use plants for as food, but also to produce oxygen and scrub CO2 and purify water. So there's a lot of good things that plants do that complement humans. So there's a shift gradually towards that more applied aspect. So that's the wheat that you saw before kind of represents that category.
Quick check with our folks online. Do we have any questions from social media?
So we have a question from Jamers3294 on Twitter, and his question is very simply, so when will the astronauts get to eat a fresh salad?
They already have. Not from APH, the Advanced Plant Habitat, but from Veggie, which is up there currently. So that is our goal, and we continue to use the Veggie hardware that's up on station. And in fact, there's a second Veggie unit that is going up. I don't know if that was part of the briefing, but on this OA7 flight. So Veggie has about the same footprint for growing plants as the Advanced Plant Habitat. But it doesn't have the controlled environment that the Advanced Plant Habitat has. But that could be almost just as important, because as you scale up plant growth for food, you're not always going to have a very controlled environment, because it's very expensive and elaborate to create that controlled environment. So you may, in fact, have something like Veggie where you're just pulling in the air from the cabin environment and seeing how you can grow plants based on that limitation. And we've been successful in doing that, and we hope to expand upon that.
And if I can add to that real quick, so Plant Habitat has 4 quadrants. So what we could do in the future is we could plant 4 different, for instance, make a salad, lettuce, tomatoes, onions, peppers, and they all have different growth cycles. So what we could do is actually start them individually, so that way they can harvest all at the same time, and they can have a salad straight across the board as if they went to the local grocery store. So it's just an option. I'm just throwing it out there to my customer. So
Sounds delicious. We have time for one more question in the room here in the back in the green, please.
So are you considered the Mark Watney of NASA, and are you planning on growing potatoes?
We're not currently planning on growing potatoes in Advanced Plant Habitat. It's possible. However, members of our team here at Kennedy Space Center are growing potatoes in simulants of regolith, as you would find on Mars. So that work has started. In fact, it started a number of years ago. It's not that we just started it, but that's an ongoing effort. I can't claim to be Mark Watney, though.
I don't think anybody can, but Mark Watney. All right, thank you both. Appreciate it. Thank you for the show and tell. He brought what, guys? Gonna get it right?
Arabidopsis.
So much better, but not quite together. Thank you again. And our next guest is Saurav Sinha, and he's going to talk to us about ADCs and microgravity, and starting with what that means exactly.
Well, thanks for having me here. It's really great to be here. We've been working on this project for about 2 years now, so finally seeing it come to fruition and getting ready for takeoff here. So what we do, Saurav Sinha, Chief Executive Officer of Oncolinks Pharmaceuticals. When what we do is we develop targeted cancer drugs that don't have any nasty side effects of chemotherapy. So what that means is we take supercharged chemotherapy, we link it to a carrier molecule, gets carried directly to the cancer cell, and then binds onto that cancer cell, releasing the drug just to the cancer cells and not the healthy cells. So that's really a way to avoid all those side effects like nausea, hair loss, the anemia, all those other nasty side effects that are commonly associated with chemotherapy today. Now, what we really hope to do on the International Space Station is bring some of that microgravity environment and the unique microenvironment of the tumors in microgravity back here on Earth. So basically, when we do research on Earth, we have those cancer cells laying flat in a petri dish. But that's not really how tumors evolve or grow in your body. So solid tumors actually form these spheroids. So in microgravity or no gravity, these cells will float around and they'll bind onto each other and they'll actually form these spheroid tumor models. And basically, the microenvironment of those spheroids are very, very different than what you would find in a petri dish where the cells are just laying flat. The inside of those balls are very, very hypoxic. There's no oxygen that gets into the middle of those spheroids, and actually the tumor cells are actually dead, so it's only the outside of the spheroid and the solid tumor that's actually growing. So what we really hope to do is study that microenvironment, figure out exactly how our drugs are metabolized in those solid tumors, so that way when we move into clinical trials, hopefully in the next couple of years, we'll have a better understanding of which drugs work the best for which tumors, and how we can really optimize these drugs to treat as many patients as possible. So with that, I'd like to thank NASA, I'd like to thank CASIS, I'd like to thank the University of Buffalo, BioServe, all our partners, and the University of Houston who've partnered with us on this, and I'll open it up from questions for there.
Great. We'll start with questions from the room. Right here in the second row, please.
So on Earth with the 2D Petri dish, apparatus, we know you put the film and you look at it through a microscope. So how does that apparatus change, or how does that look differently in capturing that in 3D in space?
Great. So maybe this would be a good time to bring up the slides, and I can answer that exact question. We'll go to the first picture. So basically, we have these biocells, and that's exactly what I'm filling there with Luis Zia, who's a really great engineer from BioServe. He did a lot of great work for us. And in these, what's called biocells, the cells will be deposited there. They'll float around. We actually put in magnetized molecules that help the spheroids form much quicker, so then we can get to testing them much quicker. And basically, we'll use microscopy and fluorescent microscopy to really image the cells. And we can actually see these spheroids forming over the course of days. They'll start to form very small, and then once they sort of latch onto each other and form these initial balls, then they grow very rapidly from there. And then we can go to the next slide. The next picture there, that's Luis Zia, myself, and Matt Vallone, another BioServe engineer. That's the PHABs, the biocells, and our syringes with all the drugs and cells loaded into them. So those are the last human hands that'll touch them here on Earth until they're opened up on the International Space Station. So any other questions?
Question right here in the front row, please. Just wait for the microphone.
Do you have any particular type of cancer that you're targeting right now, or are you just doing generally all different type of tumor cells?
Great. So great question. So the cells that are going up on the International Space Station are lung cancer cells. But what's most unique about antibody-drug conjugates is that we have that targeting molecule that will carry that supercharged payload right to the cancer cell. So if you swap out that targeting molecule, you can actually carry it to lung cancer or breast cancer or colon cancer, kidney cancer, and so on. So you can actually target many, many different cancers using just one targeted molecule.
Great question. As a reminder, if you're watching online, please use the hashtag AskNASA to submit a question. Sarah, any questions? Anyone else in the room? Anything else to add, Saurav?
No, just looking forward to launch tomorrow.
Sounds good. Thank you very much for being here today.
Thank you.
And our next guest, we're going to hear about Genes in Space, a student experiment. This is Julian Rubenfein, and we have Dr. Sebastian Craves from Genes in Space.
Thanks very much. Genes in Space is a national science competition inviting students in middle school and high school to design a DNA analysis experiment that can help us tackle a question posed by space travel, an opportunity or a challenge of space travel. And every year we invite kids in grades 7 through 12 to respond to this challenge by designing an experiment that utilizes the unique capabilities and microgravity environment of the ISS. Last year, 2016, we received over 380 proposals representing around 1,000 participants from across the country. And the top 5 were invited to receive mentoring from scientists at MIT and Harvard, and they came to present their projects at the International Space Station R&D conference in San Diego, where Julian Rubinfein emerged as the winner. Today we will hear directly from Julian about his experiment to not only answer a fascinating and relevant question about space travel, which is what happens to the end caps of our chromosomes as we travel through space, but Julian's experiment is also helping us build further capabilities for molecular analysis aboard the ISS. And it's been a really fascinating year, 2016, for molecular biology in space. I'm a molecular biologist, so I get very excited about this. We had the first DNA amplification experiment successfully carried out. This was also designed by a high school student, the winner of the first Genes in Space competition, Anna Sofia Bogorayev. And we also had another major milestone, which was the biomolecule sequencer payload, carrying out the first DNA sequencing experiment. And these two techniques are really significantly enhancing capabilities for DNA analysis in space, and together they're game-changing for space exploration. So in this payload, we're having the luxury of not only flying Julian's winning experiment, but also combining the mini PCR and the MinION sequencer together. The biomolecule analyzer project was carried out independently of us by a group at NASA Johnson Space Center that we've since started collaborating with to enable the complete workflow to allow us to take a sample on the ISS, amplify DNA, sequence that DNA, and answer what microbes are coexisting with astronauts on the ISS. So Genes in Space, for context, is a collaboration, a partnership between several companies. Mini-PCR, we're the makers of the DNA amplification technology that serves as the basis for the competition. Boeing, Cases, New England Biolabs, and MFA. And it's extremely exciting that a partnership between private sector, biotech, aerospace, space agencies, and the public is helping push forward the space research agenda. And we're extremely proud to introduce Julian Rubinfein, winner of the 2016 competition.
Great. Hi, everyone. Super excited to be here. This is pretty cool. Love the flight suit. That's amazing. And it's great audience, teachers and everything. Really pumped for the launch tomorrow, or April 18th. Fingers crossed. Love all of the science. Arabidopsis, huge fan. ADCs, I love, immuno-oncology, all of that. So I'll talk a little bit about the science that we're going to be setting up tomorrow, April 18th, fingers crossed. Right here, I have a little nifty machine. It's called a mini PCR machine. And I'll go into all of the details and everything, but sitting on the Cygnus spacecraft right now, on the ground is one of these, and there's some tubes alongside it that are really similar to these, and I'll tell you all about those. But when our astronauts on the space station receive these things a few days from now, they'll be able to run a preliminary test of an assay that scientists will be able to use in the future to investigate telomere dynamics aboard the space station. So I'll explain all of that. I'll get into the weeds. You can tell me if I'm getting too technical. Huge nerd. I love all of this. But I'll just contextualize it first a little bit. So, the next sort of great journey for mankind in terms of manned space exploration is, of course, the manned mission to Mars. That's what everyone's pumped about. That's what, everyone's excited about. Everyone's working on that. But, day by day, it's becoming more and more clear that humans aren't, you and me, we're not, biologically primed for that kind of long duration mission. So, if we send astronauts up to the space station for a short mission, 6 months or something like that, they go up there and they encounter really numerous, significant health problems. So we're talking about things like, increased risk for cardiovascular diseases or atherosclerosis. I mean, everyone knows about like the loss of bone density and all of these types of things. They're really serious. So And everyone also knows that if you increase the mission duration to something like 9 months to go to Mars or something like that, and you're going into deep space with more cosmic radiation, all of that, the symptoms get worse and worse. So it's important that we understand astronaut health before we attempt something really ambitious like that. So the current platform for doing that kind of research is the ISS, of course. Super cool. And over the last few years, the volume of molecular biology research, specifically on the ISS, has increased exponentially. And likewise, the data that's come down about physiological, genetic, epigenetic, transcriptomic, metabolomic changes in astronauts, everything from the microscopic level to the macroscopic level, that's increased exponentially as well. So we're learning a lot. And what I've been focused on, for the past year or so with all of the people who've been assisting me is really a very specific genetic change that can occur in astronauts when they go to space. And that's a change in the regulation of their telomeres. So I have a little visual here. This is just one of my shoelaces. So if you try to think, it's fine. If you try to think of a telomere, a good way to think of a shoelace, it's sort of a protective cap made out of DNA and protein. We would say a nucleoprotein cap. It's repetitive on the tips of all of our chromosomes. So, all of our cells, they have chromosomes, 46 of them, and on the tip of each of one, there's a little telomere. So if you think of the shoestring like a chromosome, then the little plastic tip, the aglet, I think is the term, is like the telomere. So it protects the shoelace from fraying. Telomeres protect chromosomes from all kinds of damage that can be incurred in a cell, all types of things all the time. So they're obviously really crucial. And likewise, you can assume from that the regulation of telomeres, especially telomere length, so whether they're too long or too short, that's something that's really closely controlled in a cell. That's really important. So there's been a lot of research on Earth into what happens when the length of a telomere especially gets out of whack. So aberrant regulation of telomere length, that's a big thing. And there have been a lot of sort of connections to a lot of diseases that humans experience on Earth, especially in the elderly population. That's because our telomeres get shorter naturally as we age, depending on the cell type. So we're talking about things like cardiovascular disease, again, different cancers, insulin resistance or poor immune function, all of these types of things. So NASA is really interested in this. And that is primarily because when astronauts go to space, all of the stresses that they go through, microgravity, cosmic radiation are the big ones, but poor quality of sleep. It's really hard to sleep in microgravity, apparently. Poor nutrition. All of these things lead us to believe that the regulation of their telomere lengths in different cell types within their bodies, that is sort of weird, sort of wonky. That gets, sort of out of whack, like I said, when they go to space. So it's something NASA's interested in, and we know that's true. The telomere regulation in space is abnormal in some people, because when Scott Kelly came down from his almost year in space a few months ago, in some of his blood cells, preliminary data shows some of his telomeres got significantly longer, which is kind of a weird result that's kind of difficult to explain right now, but it's really interesting. And meaningful for future spaceflight. So that's why it's important to study telomeres. When I was thinking about this last year, the next question was really, what's the best way to go about looking at something like this? If you're a team of scientists and you're interested in telomeres, how do you do that? Well, if you're like the scientists who looked at Scott Kelly's telomeres, you prepare materials on Earth, you ship them here to KSC, you put them on the rocket, lift off, you collect samples in space, you have to prepare those, you send that, you ship it back to the lab, all of that. And that's worked fine and it's been great, but you can imagine how when you scale something like that up to a longer duration mission, it quickly becomes inefficient. So there's a bit of a bottleneck there for this kind of molecular biology research. So the holy grail, so to speak, for this kind of thing is a platform where we can do these kinds of investigations on the space station in real time on orbit without having to send stuff back and forth, giving astronauts full autonomy. So I'll just talk super quick about this. Sorry. So this is a mini PCR machine, polymerase chain reaction machine. Basically, what we do is we get these little tubes like this. We add water, we add DNA, we add enzymes, and we put them in here. Turn the machine on a few hours, and the machine will actually copy the DNA billions and billions of times. So we can do this with telomeres because telomeres are mostly DNA, and we get tons and tons of telomeres that we can then analyze. So that's important, and this is actually small enough along with this that we can use it on the space station. So we send these up, and eventually astronauts will be able to isolate DNA on the space station and perform this kind of assay, gather all kinds of data. You can think of setting up model organisms like Arabidopsis, or we also have mice up there, yeah. Like little, rodent astronauts, all types of things, periodically keep them there for generations. You can do this with astronauts too. Collect their DNA over time, have them perform the assay on themselves, gather all kinds of data that we've never had before. So really
Thank you,
exciting.
Julian.
Yeah.
I don't want to cut off somebody so much smarter than me, but holy cow, do you guys know that he's 17? 17?
16.
16 years old. Oh my goodness. Excellent briefing. We have time for just one or two questions if we have any in the room, please. We'll start right here in the front row.
So I said, by the way, congratulations. That was very impressive.
Thanks. I hope it made sense.
Yeah, sort of. Okay. So, like I said, I teach 5th and 6th grade at Little St. Barnabas, Indianapolis, and then I'm also part of this program called the Trustee STEM Teaching Fellows with the University of Notre Dame. So I have students in middle school all across the country are watching this right now. What would you say to them to get them to sort of,
yeah.
as an inspiration that you are, like, what's your message?
Okay, I mean, to do this type of work, it's actually a totally unique opportunity. I can say kind of easily that the field of space science and space biology is so nascent that it's actually possible for me as a high school student to make a significant scientific contribution to really advance human knowledge, in a small way, but that's more than enough. I mean, you don't have to be a professor or a career government scientist or something. There's so much that needs to be done before we can do a Mars mission that it's like all hands on deck, So if you come up with something creative or something that, nobody's even been able to do yet, there's all sorts of opportunities.
Great. Any more questions in the room? Question from online?
Okay, so I have a question from Twitter from Lauren Aloise, and her question is, what is amplification of DNA mean, and how is this done? Can you look at telomeres and their action?
Thanks. I had to rush through that part. I'm sorry, but amplification is like what I said. You throw the telomeres into this machine here, you turn it on, and amplification is when you make billions and billions and billions of copies of that DNA. And DNA is such a small molecule that to do any kind of real analysis with it, you have to have a lot of it. So it's an essential precursor to any kind of analysis technique that we need. So the reason that this is what we're doing in the mission tomorrow before we can do the full assay is that, as any molecular biologist will know, not all PCR target sequences are created equal. So a really repetitive region like a telomere is going to be tricky to amplify on Earth, to make a bunch of copies of, not to mention microgravity. So we're just testing this out. Did that answer the question? Okay, great.
Any more questions in the room? One more time. Up front here.
I just want to know where you go to school and what kind of school and how did you do this during school?
Yeah, I have had to balance this. I have a few tests when I get back. A couple of days from now, actually. I haven't started studying. So I go to Stuyvesant High School in New York. It's a math and science school, but I also love reading and writing in Lower Manhattan. This was mostly done outside of school. This was something I initiated myself after talking with my teacher about it a lot. And then it's been, working in labs all over the East Coast, since then, at NYU, at New England Biolabs, our partner.
And I'll just add, this is an annual competition that we run every year, and it's currently open for its 3rd year of submission. So students across the country in grades 7 through 12 have until April 25th to come up with a killer idea. And they can be standing right there next year.
Great. Well, thank you so much, and congratulations again, Julian. We're just going to hold for a second for our next guest. And now we have Henry Martin and Davide Masudi to talk to us about some of the CubeSats that we're sending to station.
Yes, good afternoon, everybody. My name is Henry Martin from Nanorex, and today I'm going to talk mostly about the satellites in which we are launching up to the ISS on April 18th. So I have some slides. Could you throw them up there? Cool. Anyway, so Nanorex, we don't only launch small satellites. We do a lot of stuff on the ISS. By the April 18th launch, OA7, we will have sent up over 550 science experiments to the ISS. They'll range from internal research, so plants, DNA, all sorts of different things, to also satellites, things on the outside of the station, etc. Tomorrow we'll be debuting mostly the top two, so the CubeSat deployer, which goes out of the Kibo airlock, which is run by the Japanese component of the ISS, and then we'll also be using the outside of the Orbital ATK CRS vehicle to launch at a higher altitude. Next slide. Cool. So we're launching 38 satellites total, and 34 of them are going to be through the inside. So this is a shot, just an example of we shoot out anywhere from like 1 to 3 at a time, and then they go off into space and do whatever they were meant to do. There's a broad range of things satellites can do, really anything, and right now they're getting a lot smaller. These are 3 CubeSats here. Next slide. Here is a snapshot, cool picture of the external CubeSat deployer that we have. So there's a white box kind of on the left, bottom left. We actually mount that on the outside so it never goes the inside. Crew never has to touch it. Once the Cygnus leaves, it will, pending all nominal operations, go to a higher altitude and shoot them out, giving the CubeSat customers more lifetime. These CubeSats here are going to do commercial weather, so they'll take the data and they'll sell it to people who ever need to track ships, and they also track ships themselves. So like AIS receivers, most of them are ground-based, and once it goes about 60 miles offshore, you can't really track the ship. If you put it on a satellite, you can track it wherever it goes. So next slide is really here my colleague and partner Davide Masudi. 28 of the satellites we're launching internally are part of this QB50 mission. And QB50 is a very cool mission, which you will hear about from him. But what's cool about this slide is it is a huge collaboration effort among engineers, scientists, all sorts of people who made this happen. They've been working on it a very long time. I personally, with another colleague, have been going at it for about 2 years now, and we are very excited to get it up. So with that, Davide.
Thank you, Henry. So good afternoon to everybody. We're very actually excited to be here. We're coming from Europe to present you this project. So can you put the slide, please? So QB50, it's a real international project. We are going to launch a constellation of CubeSats, 28 for the precision, to investigate the mid-lower thermosphere. Next slide. So the 28 CubeSats, in fact, are manufactured and designed by students, universities, coming from all over the world, literally all 5 continents. We have more than 15 countries involved in this project. So in fact, it's a truly international collaboration. So the project is coordinated by a consortium led by the von Karman Institute for Fluid Dynamics and received funding from the European Union. Now we have 15 partners taking part of the consortium, 15 professionals, in fact. So when the project was conceived, we conceived the project with 4 objectives in mind. The first is facilitating access to space. So we're providing students and universities easy access to space. So what we do basically is we're following them, we are supporting them from design to manufacturing to integration and launch. So we're providing them support, technological support for designing their CubeSats. Then we do also orbital, so in-orbit demonstration. So we have, of course, students designing their own CubeSat, testing their own technologies, or we're providing a platform for in-orbit demonstration. We're also doing education. In fact, what we do is we are trying to educate future research and space engineers So we're also fostering international collaboration, which is the most important part in QB50. And lately, and the last, in fact, we do also science. That's why we're here. So what we do is we're trying to launch a constellation of CubeSat to investigate the lower thermosphere. Now, why we're doing that? So the lower thermosphere, in fact, is the mostly unexplored region of the atmosphere. It runs between 200 and 400 kilometers altitude. In fact, the lower thermosphere is too low for big satellites. In fact, it's lower than the International Space Station, but it's also too high to be reached by rockets, small rockets, in fact. So CubeSat provides the perfect mean, the perfect way, the perfect tool to explore, to do in situ measurements of the thermosphere. So provides the tool, in fact, to do these measurements. So what we do, in fact, we have the CubeSats, which built by the universities and students, and then as a consortium, we provide them an instrument. So all these satellites, in fact, has one instrument provided by the consortium to measure the chemical composition of the thermosphere. So now, why it's so important to analyze the thermosphere, the mid-lower thermosphere? In fact, the mid-lower thermosphere is the area in the atmosphere where the space shuttle flies, for example. Of course, you have a lot of space debris, and you have a lot of satellites there. So, thanks for the slide. So, in fact, knowing the density, in fact, will provide us a better knowledge of the thermosphere, will provide a better tool to predict, for example, assess the trajectory of space debris re-entering the atmosphere, for example. And we also provide better tool for predicting, for example, station-keeping maneuvers or collision-avoid maneuvers for the space station, for example, or other satellites. And the late also, of course, all these results that coming from the constellation of sensors will also provide a database that will be used by scientists for many years, will be used for enhancing modeling, forecasting modeling of the thermosphere. In fact, most of the, the models are physical models, and in fact the knowledge of the physical, so the chemical composition, also the electrical phenomena in the thermosphere will in fact help scientists to do better modeling of the thermosphere. Now, if you go to the next slide, please. Right, here we have a lot of the CubeSats. We have 28, in fact. All of them are different from each other. So, in fact, during QB50, we tremendously learn that the same objectives can be, or the same objective, in fact, can be reached by 28 different ways. So we have 28 CubeSat. Each of them, as I said, has a single science payload on board, an instrument provided by us, and all of them will contribute to create this database. So in fact, what we're going to have is the first coordinated in situ measurement of the thermosphere. Okay, and this is also the first international collaboration where we are coordinating basically CubeSats from all over the world, in fact. So just to conclude for the next slide, please. So QB50 has a number of firsts. We have 28 CubeSats in an international collaboration. So actually, it's a constellation that will provide us with multi-point measurement of the thermosphere, of the lower thermosphere. There are 3 sensors, as I said. There is a ion neutral mass spectrometer, a flux probe, and a Langmuir probe to measure different chemical components of the thermosphere, also the electrical content of the thermosphere. We receive fundings for 9 million from the European Union, but in fact, this covers only the launch and the support. But you have to consider that all the rest, so the bus, the CubeSat, have been manufactured by universities. So in fact, if we think about how many universities, how many people we involved in the project, we can think about having involved at least more than 50 professors. I suppose this is really the lower boundary of my estimation, and more than 300 students that were involved in this international collaboration. And we also produced an average of 10,000 pages of documentation, which in fact we had to review. So, so we are very proud of this mission, of course. We tremendously learn, and we're extremely excited to be here today. Thanks a lot.
Great, thank you both. Unfortunately, we're right at the top of the hour, but we could sneak in one quick question if there is a question from the audience right now. Right here.
Hey, I'm Doss with the Kerbal Space Academy. We've been talking about CubeSats and the size of CubeSats and stuff, but a lot of people don't really have an indication of how big a CubeSat is. My question is about how big are these CubeSats you're talking about, and would my little guy here fit?
Sure. Well, the CubeSat we are talking about can be modular, but the CubeSat we are talking about is a shoebox size. Yeah, shoebox size. It would fit.
Oh yeah, he could go. He
could go. Yeah.
All right. Thank you, Henry. Thank you, Davide. I believe you'll be around later if there are additional questions.
Thanks, everybody.
Thank you,
NASA.
thank you.
That is going to wrap up our What's on Board briefing part 1, talking about the science that we are sending to the International Space Station aboard a Cygnus spacecraft. Again, our launch is targeted for April 18th at 11:11 a.m. when a 30-minute launch window will open. If you're watching live, please stay tuned. In another moment, we'll come back and we'll discuss the Atlas V rocket and the Cygnus spacecraft with mission experts. Thanks and have a great day.
Hi, everybody, and welcome back here today to NASA's Kennedy Space Center, where on April the 18th at 11:11 a.m., we're going to be launching the Orbital ATK's Cygnus spacecraft carrying cargo and supplies to the International Space Station. For those of you who are just joining us, we are here live and going to talk a little bit about the spacecraft and the rocket that it's going up on, which is a United Launch Alliance Atlas V rocket. And so joining us to talk about some of this, though, jumping straight into it here from the United Launch Alliance, is Joe Fust. If you want to follow them on social media, you can follow them at ULA Launch. And so without further ado, let's talk about the rocket.
Thank you. Thank you. All right, so I have some slides to pitch. And so and so if you can bring up the first slide as I'll talk. My name is Joe. And I'm with United Launch Alliance, and I'm representing launch operations. I've worked many different systems on the rocket up into my current position as spacecraft integration. And so we have a picture of our rocket here in separated sections. And this rocket will provide the high-tech muscle for tomorrow's launch. And you can see the first section is a brown section, like a tan color, and that's the Atlas booster. With the RD-180 engines attached to the bottom with the engine thrust section at the bottom. The interstage adapter, and then the second stage Centaur. Now let me stop right there. The booster and the Centaur are made in Decatur, Alabama, and shipped down, and then dropped off at the port and delivered to us for processing. The interstage adapters and the payload fairings are made in Harlingen, Texas, and shipped over to us. We process all of these in a combination of 4 or 5 different buildings. Get it all ready. We erect the Atlas booster first in the VIF, in the Vehicle Integration Facility. The interstage adapters, the second stage comes over. We put that up on top and get ready for the spacecraft, which is being processed in its own facility. Get ready to go. It is encapsulated, and the encapsulated assembly, we call it, the payload and the fairings, come out together and get set on top of the rocket about 2 weeks before we launch. The whole launch time is about from launch from 11:11 to about 4 minutes in, 4.5 minutes in. The whole booster is done and it separates. We're left with the Centaur, the second stage, which burns for the rest of the time until separation, typically 30 to 45 minutes from T0, from launch time, and we're separated. And our muscle part is done. So we're done in less than an hour, easy. And we put you in orbit, and the spacecraft finds its way home, whether in this case, off to the space station to be mated with the space station. Second slide. So this is the launch complex. Right now, this is it's a perfect representation of what's there right now. That was rolled out this morning. Started at 8 o'clock. The vertical integration facility is the building that's off to the left-hand side of the picture. It's about a 1/4 mile away from the center of the launch pad. The whole trip took less than an hour to roll out. It's walking speed that it rolls out at. It sets right in between these 4 lightning tower masts that protect it from any lightning for the night's stay out there. We roll out typically the day before we launch. And then and in the afternoon today, matter of fact, we filled the booster tank with RP1, that's highly refined kerosene. Tomorrow we'll do cryogenic load of liquid oxygen and liquid hydrogen in the rest of the first and the second stage. And then and we start that about 2 hours before we actually launch. So there's lots of preparations to be done. The guys will come in, the whole crew will come in probably early in the morning, more like 2 o'clock and 3 o'clock in the morning to get ready for that last 2 hours cryogenic load and launch. I believe we have a video. If we can play that now.
The following profile details the important events of this mission using approximate times.
5, 4, 3. We have Atlas ignition. 2, 1, 0, and liftoff. We have liftoff of the Atlas V rocket.
The Atlas RD-180 main engine ignites to lift the vehicle away from the pad. Shortly after liftoff, Atlas begins its initial pitch, yaw, and roll maneuvers to attain the proper ascent profile and minimize aerodynamic loads. The Atlas V reaches Mach 1, the speed of sound, at 83 seconds. At 94 seconds, the vehicle experiences maximum dynamic pressure. Approaching booster engine cutoff, the Atlas V is spurting propellant at the rate of 1,350 pounds per second, traveling at approximately 10,000 miles per hour, and located 79 miles in altitude and 172 miles downrange. Booster engine cutoff occurs 4 minutes and 15 seconds after liftoff. 6 seconds after booster engine cutoff, the booster stage is jettisoned. The first Centaur main engine start takes place 10 seconds after booster separation. The payload fairing is jettisoned approximately 4 minutes and 40 seconds into the flight. Cutoff of the Centaur main engine follows a nearly 14-minute burn. The mission now enters a short coast in preparation for spacecraft separation. At 21 minutes, Centaur releases the Cygnus spacecraft for Orbital ATK and NASA.
And that's a mission profile. Thank you very much.
All right. Wonderful. So we are going to now talk about that particular spacecraft that was there at the end of the video. And that comes from Orbital ATK. If you want to follow them on social media, you can find them at Orbital ATK. And without further ado, here's Paul Escalera to talk all about the spacecraft. Paul?
All right. Thank you. Good afternoon. Can everybody hear me? So I work at Dulles, Virginia, which is where we manufacture the Cygnus spacecraft. And so I'm supposedly know everything you guys want to know, but we'll see. And let me point out, as all of you are, we're very excited to be here, especially on the eve of a launch. This one's kind of been a long time coming, so we're very excited, you know, to get this off the ground tomorrow. So I do have a video that I'll speak to, so why don't we go ahead and cue that. And this video will tell us a little about Cygnus, its cargo, and its mission. So it'll first start with a view of Cygnus itself and our OA7 mission patch, which is shown there. So as you know, we'll be launching Cygnus for the 3rd time on an Atlas V launch vehicle. And here's some video from one of the last times we launched Cygnus on an Atlas. And Cygnus is loaded with about 7,600 pounds of cargo, which is a lot. And we expect to be at station for about 90 days. So we'll get to that later. So Cygnus is comprised of 2 modules. First shown here is our service module, which is manufactured at our Dulles facility. It has all the brains, the propulsion, the guidance and navigation and comm systems necessary to do the mission. So you see here, it's a pretty complex looking spacecraft, but it gets the job done. Our other module or piece of Cygnus is our pressurized cargo module, and that's manufactured by Thales Alenia Space in Italy. And shown here, it's arriving at the launch site. And this is where we put all the cargo, at least the pressurized cargo. So upon arrival at the launch site, we load some cargo in, and we prepare it for mating with the service module. So the service module will arrive at the launch site about a month later. And as you see here, we're mating the two pieces together. So this will make the whole Cygnus spacecraft. After mating, we load it up with fuel, and we do another final cargo load into the spacecraft and prepare it for launch. You'll notice our PCM is very large. This is our enhanced PCM. It's what we've been flying since OA4, so it carries a lot more cargo than some of our earlier missions. The service module itself is also optimized for this mission, and it features our innovative UltraFlex solar arrays, which are shown here in deployment, and these are manufactured at our Goleta plant in California. So once we arrive at station, the crew opens us up and starts unloading all the valuable science and cargo, fresh food and things of that nature, and then they fill us up with trash. Once that's done, they send us on our way. However, our mission is not complete. We still have some secondary objectives, and we have some secondary payloads on Cygnus, which include the Sapphire 3 fire experiment, which studies fire propagation in zero-G, and here's some video of from one of the last times we flew Sapphire. Very successful mission. As you heard earlier, we'll also deploy some CubeSats out of the externally mounted NanoRacks deployer. And then finally, we'll also have the Red Data 2 flight recorders on board. And these flight recorders will record the environments while we're re-entering into the atmosphere. So pressures and temperatures and things of that nature. However, in order to execute this part of the mission, we got to deorbit Cygnus. So we'll do that, and we'll safely dispose of Cygnus over the ocean so nobody gets hit by anything. So finally, you know, we're very excited to support the ISS and its crew by delivering cargo, science experiments, and also doing these secondary missions like Sapphire and these CubeSat deployments. And we do look forward to missions beyond this one, as we have many more lined up and ready to go. And we look forward to supporting ISS and NASA. So go Cygnus. Thank you.
All right, everybody. For those of you who are following along online, we're getting ready to enter into some question and answer here. You're welcome to ask questions using the hashtag AskNASA, and we'll also take some questions from here in the room. Questions all about the rocket and the spacecraft. So who's got the first question teed up? Who's ready? All right, we're going to start down front here in the orange, and then we'll work our way back and around.
Hi, Valeria Rodriguez from Miami School Gulliver. And I wanted to know, when the video was showing that all the different pieces were coming apart, do those get collected and reused, or where exactly do those pieces go?
So every part on the Atlas V is expendable, right? The booster drops off into the ocean. The Centaur will eventually deorbit and drop up to the ocean, much like the spent cargo module. And the fairings, when they separate, they fall off, and they fall off into the ocean. They come out pretty soon, so they all fall into the Atlantic. So it's an evolved expendable launch vehicle. That's the expendable part.
All right, next question will be in the second row here in the black shirt.
Hey, Lincoln Neely from Dallas. And I was wondering which part for both of y'all is the most sensitive part of the process, prone to error, and have y'all ever experienced any critical alarms or, very serious possibilities of failure and had to do some real-time problem solving in the launch or in the space vehicle?
I don't know about Joe, but we never have problems. But no, I'm kidding. Throughout the build of these spacecraft, we have to understand that they're very complex. And oftentimes you do a test that you've done 50,000 times before, and something doesn't go quite right. And we have processes in place, to investigate what the problem is and why it occurred. And the team is very skilled in executing those processes, not because we have lots of problems, but because that's how we do our business. And, so we roll with the punches. We always want to meet our launch schedule. These guys are ready and waiting for us, so we have to get through these failures as they come. So, there's always something going wrong, but we have a very skilled team that can overcome those problems.
And the launch vehicle can ditto that. We have a very experienced launch team, and anything that comes up, we can solve. And the part that really gets tense for us is when you integrate operations. When you're done with your processing your spacecraft and you're fueled, and you hand it to us to encapsulate. And that's your baby. And you don't want us to break it, and we will not. And we work together. It's integrated operations. We work together to encapsulate and transport out and carefully pick it up and set it on top of the launch vehicle. Very critical day. It's a 24-hour day plus day that we do that. And then once that's on there, we do a couple of integrated tests, make sure everything's all connected right. And the last day, the launch day, is almost the easiest day. Right. We're back to where everything is ready. The trigger is set. We just have to sit back and load it with fuel and launch. It's the easiest day.
All right, next question's in the back here.
Hi, Amy Stilling, producer of Nature Play Film. I have a question about the Sapphire project. What questions are you hoping to investigate and get answers to with Sapphire?
Great question. Well, let me start off by saying the Sapphire experiment is from NASA Glenn Research Center. So we integrate that experiment into the pressurized cargo module, and then we work with them post-departure to execute that experiment. I'm not going to necessarily speak for them. However, I will say that they're trying to understand how fire moves and propagates in 0G for different materials and different accelerants. So these samples that they have, in some cases they have more than one sample that they set on fire. They're just trying to understand how these things burn, how much smoke they get, and things of that nature. And for us, it's also a good chance for us to test our smoke detector on Cygnus. So,
all right, wonderful. There were questions over here. We'll start here in the blue.
Hi, my name is Brian Lauer. I'm from Boston, Massachusetts, here with History View VR. We were wondering, based on the history of rockets, seems like they're getting bigger and bigger. Are you guys considering having smaller rockets for microsatellites, or just in general, just downsizing the size of rockets?
So what we've been trending towards is multiple payloads, either 2 heavy payloads on one mission, or like this, a large payload and many microsatellites, many CubeSats. Yes, we have extra capacity, and as we evolve and actually get our rockets even bigger and more capacity, we'll put double satellites on and go to 2 different orbits, and that's how we'll save there and lower the cost per launch that way. And then still, we'll have extra capacity and be able to launch CubeSats for educational purposes and the like.
All right, we'll come down front here next.
Hi, Peyton Wilson from Wiregrass Ranch High School. I was wondering, just start to finish, like drawing on a scratch board, how long does the whole process of developing the rocket all the way up to launch take?
The design of Atlas V until we first launched in 2002. ELV, I'm trying to think when that started. So I'd say it was, I'm going to go out, probably a 6 to 8 year process by the time when we started the designs on paper and actually had our first launch. So it's evolved expendable. So we evolved the Atlas V from previous Atlas IIs and Atlas Is, and we developed built a new engine on an Atlas II, and then a higher tech Centaur, increased its capacity. So it started to evolve into an Atlas V until we put a new tank, different avionics, a different payload fairing, and where it was an Atlas II is now an Atlas V. And it happened in a step-by-step process. So it's tough to pick out a certain start point, but the starting 6 to 8 years from when we first started to when we first launched in 2002. That sounds right.
All right, we're going to come down front here, and then we're going to go to online questions next.
Hi, Claudette from the Flavor Radio. I wanted to ask you, you said that the rockets drop into the ocean. How environmentally friendly are the rockets, the pieces?
So when they drop in, they're completely, the fuels are completely depleted. So they're empty tanks with an engine that's empty, and it drops in, and they're so far out that it drops down to the bottom of the ocean, and it's very deep where we drop everything off. So, usually it breaks up when it hits the water, and it kind of can break up as it's dropping through the atmosphere as well, and the pieces, and they disperse, and it's you never see them again.
All right, with that, we're going to come to Ask NASA questions. Again, if you're following along online, feel free to shoot us a question using the hashtag AskNASA.
Okay, we have one question on Twitter from Boily35, and his question is, what job titles are involved for a launch, from planning to launch, so students can help plan their careers and futures in STEM?
Okay, so I'll start with mine. I'm a spacecraft integrator, and in order to be that, I had to work a bunch of different systems on I was a mechanical engineer, so a bunch of different systems on both the booster and the Centaur. And then in payloads too. So I worked up and down the rocket in the mechanical sense. I was a booster propulsion engineer, Centaur propulsion engineer. I was a pneumatic engineer. I was a launcher engineer. I was ground systems at the launch pad. I did all of those things. Sometimes didn't leave one job as I went to the next. I did them both. And so if you can diverse in the mechanical sense. Electrically, you can do that too. You can diversify in many different systems. You can run or integrate the whole system. When you all of those systems together, you can integrate it together. So.
All right, we've got time for just a couple more questions here. We're going to start down front here and then come over here.
Hi, Debbie Reynolds from Harrison Middle School in Pittsburgh. I was just questioning on are they called solar arrays? Is that what those are called? The solar panels?
Yes.
Could the Cygnus keep going if they didn't open, or if only one of them opened, or do you have a contingency plan for that?
That is something we've looked at in the past. I believe we've determined that we could do most of our mission objectives with some partial deployments. But as you probably noted, it looks kind of complex, but it is very lightweight, and it is very, innovative from our standpoint. So, but we've successfully demonstrated deployments over 3 or 4 missions already. So, but it is still a very critical part of the mission. But yes, we do have contingency plans in place in the event that something doesn't quite deploy all the way like it should.
All right, next question's down front here.
Hi there, Michael Eibel from Cheddar. I know today we've been talking a lot about these rockets breaking apart upon re-entry. I know SpaceX as well has really started developing reusable rockets, and we've already seen last month the first successful re-entry. I'm wondering where United Launch Alliance is in that process, and if that's becoming a bigger focus as space development continues.
I'm sorry, say that again. Say that again.
The whole thing?
You're asking him a question. Go ahead. But you're asking me. Go ahead. I'm sorry. Say that again.
No.
All right. So, so for us, right now, the Atlas V is completely expendable, and so as we develop other launch vehicles, the Vulcan's coming up, we're going to be able to capture the engines as they're done, as the booster section is done. The engine section will separate off, and we'll catch that and bring that back. The tank easily made again, and we're going to get the best, most expensive part. We're going to take that engine and bring that back. The other evolving sections, the second stage, we're going to replace the Centaur with an Aces, and that a much bigger version of a Centaur. It's not even a Centaur anymore. It's a bigger version, and it will have an extended fuel capacity. It'll be able to stay in orbit and be a space tug, so to speak, or be able to get to a midpoint between the Earth and the Moon, and be able to ferry things, payloads between the Earth and the Moon. And so we'll be able to reuse those components. So ULA is headed in that direction for reusability.
All right, last question is going to come from online over here.
Okay, this question comes from Keith SD on Twitter, and his question is, what are the reasons for Cygnus' unique solar arrays? Is surface area the only consideration? Does deployment have a high risk of failure?
Good question. If you recall, in some of our earlier missions, we had what we call traditional panel arrays. They were square, and they're typically what you see on other spacecraft that are flown today. But one of the benefits of the Ultraflex arrays is that they're lightweight. So we, in order to increase our performance, get more cargo up for same bang for your buck, if you will, we implemented the use of these arrays. And I think you'll notice if you look at other future architectures that NASA's investigating and things like that, you'll see these featured in those architectures. So because they're lightweight, Yes, there is some risk associated with deployment, but as I mentioned before, we've successfully shown that we can deploy these without issue. And if we don't, we have some contingency plans in place. So that's my answer.
All right, wonderful. With that, we are looking forward to the April 18th launch of the United Launch Alliance Atlas V, carrying the Orbital ATK Cygnus spacecraft to the International Space Station. That's happening at 11:11 a.m. There'll be live coverage on NASA TV. For more information about the mission, if you can visit www.nasa.gov/orbitalatk. And as always, join us online when we do live launch coverage on April the 18th. Thank you very much, and have a wonderful day from Kennedy Space Center.